For the past several videos, we've been studying series and focusing a lot on how to tell when they converge and when they diverge. Last video, we introduced power series, and I mentioned that they were an extremely important kind of series. And at this point, after all we've suffered with them, you might be wondering why power series, or even series in general, are so important. Well, today we're finally going to see some payoff for all this work we've been doing. The power of power series, if you will. It turns out many of the functions you've encountered all semester, or even in your whole mathematical career, can be rewritten as power series. This includes rational functions, roots, exponentials, logs, trig functions, and even inverse trig functions. For example, you can rewrite the function e to the x as a power series. This one, in fact. You can think of this as the result of trying to approximate the e to the x function with polynomials. You start with just a linear function. This works fine, but you can improve the approximation if you use a quadratic instead. But why stop there? If a quadratic approximation is better than a linear, then a cubic will be better still, and a degree 4 polynomial better than that. You can see where this is going. What if we never stop? Then, similar to how integrals were defined, the approximation keeps getting better and better, and in the limit, our polynomial becomes a power series. And that power series doesn't just approximate the original function, but actually equals it. Take a moment to appreciate this. This is absolutely crazy, and if your mind isn't blown yet, it needs to be. Maybe I can make it a little clearer if we plug in a value for x. Say x equals 1. Then we get e to the 1 equals 1 plus 1 plus 1/2 plus 1/6 plus 1/24, and so on. In fact, we found a way to compute the constant e to any precision we want. If you don't believe me, try adding up a few of these terms in your calculator. You should find it closely approximates the value of e. Isn't that crazy? And like I said, this isn't limited to exponentials. We can, in principle, derive power series representations of almost any function you can think of, even the sine and cosine functions. If you've ever wondered how you would compute, say, the sine of 1, this is how you do it. So basically, what we've got then is a way to rewrite almost any function we can think of as a polynomial, albeit an infinitely long one. And the great upshot is, polynomials are one of the simplest and best understood functions in all of mathematics. Compared to many other functions, polynomials are very easy to manipulate and compute. Heck, you can even compute the value of a polynomial by hand if you really wanted to. And now we have a way to write almost everything as a polynomial. In a way, you can think of power series as being like decimals for functions. We can use decimals to represent any real number in a predictable form, and they allow us to approximate any real number to any precision we want. Just truncate the decimal expansion at whatever point you need. In the same way, power series can be used to rewrite most functions in a standard polynomial-like form, and lets us approximate the function to any precision we want just by taking a partial sum of the series. Alright, coming back down to Earth again, I still haven't told you how you would actually derive these magical power series representations. How on earth did I know the e to the x function could be written with these coefficients? Why 6 and then 24 and so on? Well, the full answer to that will have to wait until next video, but we can already derive the power series representations of a number of functions by making use of the sum formula for a geometric series. To see how, consider the power series sigma sum from n equals 0 to infinity of x to the n. This power series is special because, in addition to being a power series, it is also a geometric series. It's the geometric series you get if you plug in a equals 1 and r equals x. This means the power series must converge when the absolute value of x is less than 1, and we can compute its sum using the sum formula for a geometric series. Thus, we get that the power series representation of 1 over 1 minus x is the series 1 plus x squared plus x cubed, and so on. In a sense, we've gone full circle. Instead of trying to write out a series as an algebraic formula, we're going the other way around, trying to write an algebraic formula as a series. Alright, that's fine and all, but this isn't worth much if the only thing we can turn into a power series is just the single function 1 over 1 minus x. Thankfully, we're not limited to just that. There are a number of manipulations we can make to this basic equation that allows us to write a whole family of functions as power series. One such trick is very simple. Substitute different values for x. You see, like when we were doing partial fractions, this equation works not just for a privileged value of x, but it works for all values of x, or at least for all values of x in the interval from -1 to 1. This means we can plug in not just concrete numbers for x, but entire expressions. For example, let's say I substitute x to the fourth in for x. Then I get that the rational function 1 over 1 minus x to the fourth can be written as sigma sum of x to the fourth itself to the power n, which, when we simplify it, becomes the sum of x to the 4n. Actually, there is one minor caveat I need to mention about power series before we jump into the examples. I said we can rewrite almost every function we can think of as a power series, and that's true, but we are still limited by the interval of convergence of the power series representation. The trouble is, the interval of convergence of a power series may not encompass the full domain of the target function. For example, if we graph the function 1 over 1 minus x, it is defined over the entire real number line except at x equals 1. But its power series representation, since it is a geometric series, only converges on the interval from -1 to 1. As long as you restrict x to being between -1 and 1, the power series and the function 1 over 1 minus x agree perfectly with each other. But if you step outside that interval, even a little bit, they no longer agree. In fact, they disagree as badly as possible. The function 1 over 1 minus x is finite valued, but the power series diverges. Now, this limitation doesn't always happen. In the examples I showed earlier, with e to the x and sine of x, it turns out the radius of convergence is infinite, and so the power series representation works everywhere. But as a general rule, remember that while a power series can be used to represent a function, it is a local representation, and is only guaranteed to be valid nearby the center point of the power series.